Okay, and you can see, for example, this planet here within the arrow bars on mass and radius, more than one model, at least 3 here of the plotted models, but they are infinite, of course, because it depends on how many layers, how much the elements are mixed, etc., etc. So here, for example, we have 3 models that fit these observations, and this means that we have degeneracy. And whenever we have degeneracy, we need an additional parameter to break the degeneracy. And also, this is also related to the fact that with one mean density, we cannot constrain the internal structure of a planet. We can just say, okay, this planet is made, so it's a rocky planet or a giant gaseous planet, so we can say which kind of planet it is, but we cannot say much more just with the mean density, which comes from mass and radius. So this is why we introduced the log numbers. So log numbers are 3 series of infinite parameters, and they basically measure the rigidity of a planetary body. So they are related to the interior structure. And in particular, they come out whenever there is tidal interaction between 2 bodies. So that can be moon and planet, that can be star and planet, for example. Whenever they are massive, more or less, at least one must be like the moon must be massive enough so that we can measure the tidal potential, or the planet must be close and massive enough with respect to the star so that we can measure the tidal potential effects. And of course, when there are tidal interactions, you have a shape response, which means that the planet or the body is not spherical anymore, but it will be elongated towards both sides, towards the radius vector where the potential is acting. And so we can measure that, but we can also measure the orbital response. So whenever you have a non-spherical body, of course, it will orbit in a different way around the star or whatever with respect to spherical body. So these 3 series of parameters, they're called Hn, Kn, and Ln, and they start from order 2, which is the biggest. And in particular, we are interested in Kn, but there have been studies to measure the H parameter from the transits, but this is not what I did. And Kn in particular, and K2, the biggest, is related to the gravitational response of the planet when there is tidal interaction, and therefore to the internal structure, because it's quite obvious that whenever a planet is made of rock, the tidal potential cannot deform it so easily, rather than when it's made of gas, for example. That's the basic description. And so there are special cases in which it's easy to get the log numbers. So whenever we have hydrostatic equilibrium, for any order of n, there is this special relation here between Hn and Kn. So whenever we have one, we can have the other for any n of the series, so any order. And in particular, K2 varies from 0 to 1.5. So 0 is whenever all the mass is concentrated in a point, which is surrounded by a massless envelope, which is quite unphysical, but it's a limit. And K2 equals 1.5. This is the highest value, and it corresponds to homogeneous bodies, so something like a star, or something like that. So what happens when you have tidal interactions, and how do we measure the log numbers? So whenever you have tidal interactions, you have 4 effects, as far as I know, happening in the orbit. So you have circularization. So the eccentricity of the orbit goes to 0. So after a certain amount of time, if there is no other perturber modifying the orbit, you will have a circular orbit. You have tidal decay. So basically the orbit is shrinking towards the star. You have synchronization between the rotational and the orbital period. So basically what happened with the moon. And what I'm studying is called periastron precession. And it's basically, again, an orbital response to tidal interactions. And it's the 4th effect. And it's basically how, as you see, the orbit shifts around this point here, which is the periastron point, which is the point closest to the star. And what I'm doing, I'm measuring this phenomenon, and from that, deriving the log number of the planet. And how I'm doing it, so periastron precession is basically a change of an angle in time. So it's one of the angles that you need to define an orbit, as many other orbital parameters. So it's omega, and omega naught is the change of this angle in time, of course, and it's made of three parts. So this one, I'm not gonna focus much on that, but it's the general relativity term, and then you have two terms related to tidal interactions. So the general relativity term is mostly related to orbital parameters such as A, the semi-major axis, the eccentricity, and PA is the anomalistic orbital period. So it's basically not the normal orbital period, but the one that goes from periastron to periastron, not from transit to transit. Then we have these two terms these are the ones I'm interested in. So they're basically made of many stellar and planet parameters, mass, for example, radius, semi-major axis, etc., etc. And they're also made of K, which is the second order log number of the planet and of the star. And inside here, we basically know everything from observations. We know the log number of the star from theories, usually. So from evolutionary theories and interior structure models of the star. What we actually don't know, of course, is the log number of the planet and the rotational period of the planet. We usually don't know the rotational period of the planets. It's really hard. And so we are gonna assume that at the end, because at the end we will have one equations and two unknowns, these two. And we are gonna assume that the rotational period of the planet, usually it should be, due to the high tidal interactions, it should be a synchronous orbit. So the rotational and the orbital period should be the same, but we can make assumptions on that. So here, just to show you how, from those equations I showed you before, how we integrated the periastron angle over time for our target. And you see how the periastron angle changes over one orbit. Okay, just oscillates, which was also really new to me, that over one orbit, the periastron angle oscillates and goes back to the origin. But then you see in 10, 50, 100, and 500 orbits, you can properly see a change. And so the basic fact is that if you have a baseline of observations which is long enough in time, you can see the periastron angle changing in time and measure that. And with the quotients I showed you before, related to the log number of the star. So just for those people that are not astronomers, maybe, I wanted to do a quick recap on which observations we use. You probably all know that, but just wanted to add a couple of slides. So we use radial velocities. So radial velocities come from the fact that the light, the spectrum of the star shifts whenever the star and the planet, they are moving around the center of mass of the common system. And so from that, we can derive back the orbit of the star and orbital parameter and physical parameter of both components. And we are gonna use this technique like a lot in my work. And this is how we model that. So basically at the end, it's just a sinus or cosinus function, as you saw, but it's made of a lot of components. So this one, V gamma, is basically the velocity between us, the telescope or the observer, and the common center of mass of the system. Okay, because they won't be fixed in time. I mean, they will move one with respect to the other. So since we had many instruments observing at our star, we had to add an instrumental offset, which is due to the fact that we don't have always the same fibers, instrument, etc., etc. And so it's another offset, and these are all fitting parameters. And this is the pure Keplerian motion. So at the end, just the star moving around the center of mass of the system. But inside here, what we change is basically the fact that omega, the periastron angle, is changing in time. So at the end, we fitted this omega here with omega 0 plus omega dot time. And omega dot is what, at the end, we want to relate to the log number. And what was also kind of new is this apparent contribution. that is basically we call it non-orbital contribution. So it's apparent, it's not due to motion. And it's due to the fact that whenever there is tidal interaction between the star and the planet will be deformed, like a rugby ball or something like that. And also the star will develop a bulge, a tidal bulge, and this modifies the shape of the radial velocity, basically. So the light we receive will be modified because of this tidal bulge. And also this tidal bulge is also rotating with the star. And so at the end, while the star is rotating around the center of mass of the system, we will have this apparent contribution, which is made of many parts. But it's also made of the log number of the star, but it's basically rotating as the true anomaly. So its period will be half of the orbital period because it's rotating as 2 times the true anomaly. And it's basically doing something like this. And this was just a comparison from a paper from 2012. So they didn't consider the fact that this term here, which is the ratio between the orbital period and the rotational period of a star. They didn't consider it, they just consider it 1, because in many cases there can be synchronous rotation, but for stars, for example, it depends. And so we added this term, and at the end, the amplitude, I mean, basically the shape of the curve of this non-orbital contribution was the same, but the amplitude was like 1/5, which is something like B, let's say, it depends, but in terms of between 5, so our amplitude was like 5 meters per second, and there was like 25, so it was something. And I'm gonna use also transit and occultations. I did not model any transit or occultations, but what I actually used are mid-transit and mid-occultation points. So these 2 points that I put here, because when there is periastron precession, they're gonna shift in time in a different way as usual. And I don't want to go too much in detail, but this was our mid-transit time and mid-occultation time models. So you can see that inside here, so these are how we fit all the list of mid-transit times depending on n, which is the number of transit, like starting from 0 from the discovery paper and so on. And you can see inside here there is omega dot as well. And inside the mid-occultation point, there is omega dot as well. So at the end, we fitted them all together. So the theory is done, finally. We applied our theory on a first case study, which is WASP-19AB. I'm going to say A, because there is probably another star in the system. And this actually is what really interesting for us, because if there is no other perturber in the system, such as a star or a long-term companion, for example, we may expect the eccentricity of this orbit that goes to 0, as I was showing you before. That in some certain time, there's going to be circularization. And with circularization, we don't have all the effects such as periastron precession and all the effects I was showing you. So for us, it's really important that the eccentricity of the orbit is not 0, and a faraway star may prevent that. So WASP-19b was discovered in 2010 through the transit method. This is the discovery paper, and it's perfect for us because of its mass, which is big enough, and its orbital period, which is short enough, and its semi-major axis that makes it really close to the star that we have. We expected something like some tidal interaction that can be measured. And this was the case. So we took more radial velocity observations. So here are all the radial velocity observations in time, BJ/dT/dB, starting from the discovery paper on, and these last ones are our new observations made by Hart, and they were not published yet, so they will be published for the first time. And okay, so you don't see much, but actually, so because the time is really long, but they are all curves as the radial velocity curve, but they are all like I don't know, because the time is really long. And if you put them all together, and so you phase fold them, you're gonna see the whole orbit, so the whole radial velocity curve. And here they are all phase folded with these with the parameters of these papers, the Dagati et al. 2021, which was the last radial velocity study before our study. And so this means that we phase folded them with a non-changing orbital period, non-changing periastron precession in time. And what we saw, you can see both from the residuals and also from the curve, is a remarkable scatter. And this tells us that, so the observations are 12 years long, and this tells us that putting the orbital period and all the parameters as fixed in time, no changing parameters in time, it's not good to describe the whole 12 years of observation, so the whole orbit. And also we took, as I told you, mid-transit and mid-occultation times. So these are just plotted there, like blue are transits and red are occultations, and they are plotted against the cycle, which is the number of orbits that happened starting from one specific orbit, which I put the first one in the discovery paper, and just the time that the mid-transit or occultation point happened. But before measuring the periastron precession, I made a lot of things, because if there is some other additional body in the system, the signal must be removed first before measuring the periastron precession, because it's gonna mix with things. It's gonna be a perturber, like in the radial velocity curve. You don't see it separately, the omega dot effects and a perturber effect. You're gonna see them together. So what I did, actually, first of all, I did a periodogram, which is a Fourier transform, basically. And what I saw, so that one is the orbital period of the first planet, what I was expecting. Then I subtracted the signal of the first planet from the radial velocities, and what I saw are, so I did the periodogram again of the residuals, and I saw two peaks, but basically the false alarm probability told me that they are not significant peaks. So I tried that before. I also did a sensitivity study. So I subtracted the signal. I both did a sensitivity study on TTVs and on RVs. So what I did, for example, on RVs, I subtracted the radial velocity signal of the first planet, and I got residual amplitude. The maximum of the residual amplitude was 52 meters per second. And from that, I derived what would be the mass of a perturber causing that residual. And with that mass, what we did was, like, we fitted our radial velocity data with an additional perturbing planet to see if there may be actually something there. Maybe that's really naive, but what I did, I kind of injected in the fitting 2 billion planets, like modeling one at a time, of course, but with 2 billion random orbital parameters that would respect these criteria. So basically, the mass of the planet, of this second planet at the putative perturber, had to be between 1 and 400 Earth masses, which is what basically the residuals of the radial velocity gave us in the slide before. And this is the amplitude of the radial velocities between 0.1 meters per second. Below we cannot go because of the error bars. They have to be, we cannot go below the error bars that we have, up to 100 meters per second. But we say that at 100 meters per second, we should be able to see something like a perturber that is causing such an amplitude. And this condition was a condition on the orbital period of the putative perturber, so that its period is not too short. It's not so it's from the Kepler's law. The fact that the planet won't go too enough to the star, too close enough to the star, so that there is some collision and the planet disappears. So what we did, we injected 2 billion random candidates, and what you can see here. So here are the periods, the random periods between here, just between 0 and 20 days, because this study was made on our data set, the new data, which had from the first measurement to the last measurement, there was a time span of 20 days. But we did the same with the whole data set. And here against the chi-square, and here again the period against the mass. And what you can basically see are resonant areas. So areas in which it's more possible that the planet is there. And those are the areas here, like where you see a lot of candidates. And the red lines here are also resonant orbits that we found, and they are taken from this paper from 2020, Cortés and Zuleta, and they studied also from the residuals. They studied what are the resonant orbits in the system, and we found kind of 3 or 4 out of 5, which was nice. And so at the end, I had the chi-square of all these 2 billion injected candidates, and I had the period, and I had to see if one of these was a good candidate. So to do that, I applied the big criterion, so the Bayesian information criterion, which tells us how to compare 2 models with different chi-squares, maybe the same data, but for example, different number of parameters. In our case, the number of parameters were the parameters of the just one planet. So the two models are like the one with just one planet to compare to the one with 2 planets. And of course, they have a different number of parameters, because 2 planets will have the double orbital parameter, basically. And this horizontal green line, they say basically, if you want weak or strong evidence that your model with 2 planets is better than your model with 1 planet, you need a chi-square below these 2 lines. So this line here is the weak evidence line, and this is the strong evidence line. So if we want just weak evidence, the fact that the 2 planet model is better than the 1 planet model, one of these points must be below that line, and none of them was. And yeah, at that point we were pretty confident that there was no other perturber in the system. So what we did was like, okay, but still we cannot describe our data with non-changing parameters in time. So what do? So we introduced a periastron precession in our model, as I was showing you in one of the first slides. And first of all, we applied a semi-grid method. So it's a method that, so it doesn't introduce periastron precession. So omega dot as a fitting parameter, but as a fixed parameter in this range. So you basically choose, which was like 90 points. And we run our code with omega dot fixed, just to see how the chi-square distribution. And so we basically varied the omega dot between 0.3 degrees per day and 0.45 degrees per day. And you can see, so it's really nice because you can see, so here are all the chi-squares corresponding to all omega dots that we tried. And you can see there are some local minima. And this one seems a global minimum. And these are all local minima. And you can see that at 0, so no periastron precession, there is a really high peak. So this is kind of telling us you shouldn't model the data with no periastron precession. At least put a -1. It seems to be better, of course, a +1, but at least put something. And also all these local minima you can see around, they show that when we let omega dot as a free parameter varying in our MCMC routine, we will find this local minima again, and this shows the complexity of this problem and of this data probably as well. So at the end, we were pretty confident to introduce periastron precession in our model, and this is what we did. So here, what I'm showing are the posterior distributions. So on the x-axis, you have the anomalistic period, and on the y-axis, you have omega dot as a posterior distribution. So I think we run 90 chains in parallel at this point, something like that. With, I don't remember, a few million steps. I don't remember exactly, but there were really many chains. So, for example, this is the distribution. It's on this other axis, but you can see this is the posterior distribution of omega dot, and you can see all here are the local minima that I was showing before, and this must be the global minimum. And I wanted to plot them together to show that they are strictly correlated. And they're strictly correlated, why? Because of this equation. There is some degeneracy between these two parameters, and it's due to the fact they are both related to the sidereal period, which should be the period between transit and transit, the other period I was mentioning before. And so it's kind of hard to break this degeneracy. And this is why we introduced TTVs, so transit and occultations, because we actually don't really need TTVs to measure periastron precessions. So radial velocity should be enough, but TTVs, so transit and occultation times, they really help to constrain the orbital period of the system.
Just as a point of jargon, a lot of our people don't know the term TT.
Okay, it's transit timing variations. So what happens, so how the transit and occultation mid times, they vary instead of like a linear trend that every, I don't know, 0.8 days there is a transit and every 0.8 days there is an occultation. TTVs happen or are not zero whenever you have some perturber in the system that maybe it's not every 0.8 days, but it's going to be every 0.7999 something, and it's going to change in time. Thank you. So yeah, this is why we introduced transit and occultation mid times and TTVs. And it's also really nice to zoom around the region here where there is omega dot equals to 0. So this is just a zoom so you can see that many chains did not really converge wherever omega dot was 0. So they just avoid this region. And this is another confirmation that we need periastron precession to describe this system. So at the end, we got 5 solutions. So what to choose? It was some kind, so we of course didn't choose the one with high chi-squares. So the one with the lowest chi-square was this one, but it's a really complex problem apparently, and did not happen with another case study, WASP-18AB. It did not happen in 2019 when my supervisor studied that system. So maybe it's the data, maybe it's the complexity of this system, and also this solution here, people online cannot see it. The highest solution of omega dot here, so deriving the log number, this would make a log number higher than 1.5, and this means this is unphysical. So the highest limit is like K2 equals to 1.5, which is a homogeneous body. And well, basically we discarded these other 2 positive solutions because the chi-square was really high, and also the negative solution. So you can see here is 0, and here is the negative solution, and so there is also a negative solution which represents basically this point here. This is the negative solution, and so what we also did. So what would a negative periastron precession mean? I would say perturbing planet somewhere that would cause a negative periastron precession. So what I did is to study what would be the mass and period of such perturbing planets that would cause that periastron precession rate negative. And this is what I produced. So this plot that shows the period of that putative perturber against the mass. And as you can see, these are already ranges of orbital periods between 0 and 10 days, and ranges of mass that we studied before in the analysis I was showing you. So basically, we could pull out that as well, and in parallel with the high chi-square that particular posterior distribution had. And so we focused at the end on the highest peak, and which is zoomed here. And the median of that peak is 0.06 degrees per day with these pretty small error bars. I'm kind of happy with that. And these are just to show you that if we phase fold the radial velocities with periastron precession with our rates, we obtain a kind of pretty convincing and not that much scattered around data, radial velocity data. And this is the same. These are so with the residuals, and these are also the residuals of the transit and occultations adding our periastron precession rate. Okay, there are outliers, but it's quite good, I would say. So at the end, we had to go back to the log number. So the equations I showed you before. So we inserted omega dot in here, in these terms here, and we derived the log number. But of course, we had to make assumptions on the rotational period of the planet, which we don't know. So we have two extreme cases. First extreme cases, the planet is not rotating. It's like not rotating around its own axis. And this is the second case here. And the first case is that the rotation is that fast that basically the planet is losing matter at the equator. So those are the two extreme cases, and we must be in between that. And the most, let's say, the most common case when there are tidal interactions, so strong tidal interactions, is synchronous rotation, as I anticipated before. So whenever the orbital and rotational period of the planet are the same, but for all of them, we derived a log number. So these are the two extreme cases, and this is the most possible solution. So at the end, we derive from those equations I showed you before a log number of 0.2, which is quite slow because it must be between 0 and 1.5. So, oh, sorry, there is something else. As a comparison, the log number of Jupiter is 0.6, and log number of planets that have a lot of mass concentrated in the nucleus, they are pretty low, like 0.1, 0.2, or something like that. So this is going to tell us that most of the mass must be concentrated towards the center of the body. During the review process, I was also asked to search for alternative scenarios. Those would be two. One was already studied by Knudson et al. In 2014, and that would be a long-term acceleration. So again, we go back to a perturber, and again, we go back to something that is causing an acceleration in the system that we don't see, but there might be something. And also tidal decay. So one of the effects I was showing you at the beginning due to the tidal interactions is tidal decay. So whenever the orbit is shrinking, and they all can happen in parallel. So I studied both of them, and for all of them, I studied for a circular orbit, long-term acceleration for a circular orbit, and for eccentric orbit, as well as tidal decay for a circular orbit and an eccentric orbit, all cases. And this is how I modeled the radial velocity. So what I added to the radial velocity curve to model that, for example, here in tidal decay, which maybe is more interesting. So in long-term acceleration, I just add an acceleration at the end of the whole model. And in tidal decay, what I did is, since k is the amplitude of the radial velocity, And I modeled it as varying in time because k is related to the semi-major axis, and the semi-major axis is the one that shrinks when there is tidal interaction. So at the end, these are the posterior distributions of these parameters. So k dot here and gamma here. So they would describe these two scenarios, but they all, as you can see, maybe these numbers are too small, I don't know, but they are all compatible with 0. So I could rule out these two scenarios as well. And I think this is my last slide. So this was just the end of my paper. So I wanted to compare log numbers found in the solar system and in exoplanets. So in solar system, it's much easier, let's say. Usually you can go in situ with a satellite or whatever, and you can measure, for example, the tidal interaction between Jupiter and a moon of Jupiter or something like that. For exoplanets, it's much more difficult. You can do periastron precession or other techniques that people do. And yeah, this is just to for a comparison. So our number is 0.2, but there is a huge range of numbers. And for now, it's not enough to. I wanted to give us statistics on that, but we don't have enough measurements yet. And this is just a summary of what I just showed you. So yeah, nothing. And what we're gonna do next is apply the same theory on WASP-43, and hopefully on WASP-12 we will have the McDonald observations in November. No.
Okay, thank you. Questions, anybody? Somebody who's watching it on Zoom can look for questions in the chat. All right.
Really nice talk. I'm curious if you have a sense of like how many hot Jupiters, some way, obviously you're not going to do it for your PhD because you don't want to be there forever, but like how many hot Jupiters you can measure this love number for, and like if you can get a population census, what that would tell you probably about migration, or if there's different populations of hot Jupiters that you wouldn't necessarily be able to detect.
Okay.
Transit star.
So I kind of have an idea. It's around more than these. It's around like 5.
Okay.
Not that many, at least for our technique, because you need many things. You need an orbit which is at least slightly eccentric, and you need a baseline of observations of radial velocity which is at least 10 years. So that would exclude a lot of planets, and you need a planet massive enough to interact enough with the star. Yeah.
Okay. Yeah.
So can you use this method to apply it to exoplanets which has size like Earth or Mars?
Sorry, again?
Is it available to use no method to match the interior of terrestrial planets like Earth and Mars for exo system?
Sorry, is it possible to match what the
to measure the interior to this K2 number?
Yes.
For smaller planets.
So it's possible in our solar system. It's possible. It was done. The problem is that whenever you have if you have like Earth-side planet, the tidal interaction is not that big with the star, and so you don't see a rate of periastron precession which is big enough to be measured, at least in 10 years or so. But yes, of course, it's possible. It depends on the sensitivity of the instruments. If you can get sensitive radial velocity data, if they're sensitive enough. But I would say if it's below 1 Jupiter mass, we cannot do it now.
I guess the planet with the best known periastron precession is Mercury, but that's almost all in the general relativistic term.
Yes, exactly.
Yeah. I have a question for you. You have the equation relating the precession rate to the love numbers.
Yeah.
And it had both the K2 of the planet and the K2 of the star.
Yep.
And they were each multiplied by K2 of the star by the radius of the star to the 5th power.
Yep.
And by the radius of the planet to the 5th power.
Yes.
So that means that you need to know that K2 of the star very, very well.
Yes, I do. So actually, in our case, this was a fitting parameter.
Okay.
Yes. But of course, if you assume it, well, it's not really precise to assume that, because, yeah.
Is it possible to measure the A2 of the star?
Yes.
Or something?
I think it's possible whenever you measure, for example, if the orbit of the star, how it's tilted, if it's tilted, you can measure that. Yeah.
Are there any online questions?
At this time.
Okay, yes.
It's not my field, but you're looking at very tiny effects, let's say. Do you consider, or is it reasonable to consider that the planet has put the moons and orbits around it?
Oh.
That's not the orbit.
Yeah, I guess so. I don't know that much about moons. I don't know if a planet that close to the star would have moons. It's really, really close to the star.
Yeah, you have to be close in, so, yes.
Yes, that maybe can happen. I don't know if the signal would be big enough to be measured. I don't know. But I don't even know how to say, okay, there is a moon, let's add it or not.
I guess the transit profiles all look very consistent.
Yes.
So if there was a moon.
You should-
Removing a little bit of light from either before or after, you can see that in the residuals. That's one way that people look for. Right?
Yes. But we don't know any, so.
Any additional questions? Okay, nice talk, Leah. Thank you.
Thank you.